Okay, so I'd like to thank the organizers for this, putting together this wonderful conference, and I'd also like to acknowledge my father, Anna Calini, and our two undergraduate students that worked on this project. And the basis for this talk is taken from the paper that recently came out of the study from applied math. So let me just give you a little background on frequency downshifting before we start. And so the Benjamin-Feir instability, where the Stokes wave is unstable to long wavelength perturbations, is well known, but perhaps a less well-known phenomena associated with the Benjamin-Feir instability is frequency downshifting. And this has been observed in laboratory experiments and in field data. And so about 10 years after Benjamin-Feir conducted their experiments, Lake and Yoon carried out similar experiments on the evolution of modulated Stokes waves. And so what they observed was that when the wave steepness was small, the wave train experienced FTU recurrence, and when the wave steepness was large, the recurrence was imperfect. And so after the growth of the Benjamin-Feir instability, energy was permanently transferred from the carrier frequency to a lower sideband. And so the dominant frequency shifted downward, as indicated by the spectral peak, the frequency corresponding to the Fourier mode of the largest amplitude. And so these experiments did not align with the theoretical predictions of recurrence given by the nonlinear Schrodinger equation. And so around that time, you have the derivation by Disty of this higher order NLS equation, which is obtained by retaining higher order terms in the asymptotic expansions of the surface wave displacement. And although it provides a more accurate description for water wave dynamics, it doesn't capture downshifting either. So the prevailing view was that some sort of dissipation and wind played crucial roles in downshifting. And the first approach was to look at linear damping, adding in linear damping to these equations, but that was not effective. And so frequency downshift doesn't occur in linear damping unless or higher order NLS. But subsequently, various distributive models, higher order NLS models, which included wind, wave breaking, or nonlinear damping of the mean flow, were shown to describe well downshifting observed in experiments or field data for specific physical conditions. And so recently, Harder and Gauvin derived a viscous higher order NLS equation, which was identified as a good model for describing frequency downshift observed in the absence of wind and wave breaking. And so that's the equation that we will be looking at today. And so I guess I'm not getting this. Oh, it's right there. Okay. So if you let gamma and delta be zero, then the three terms that you have within the brackets here are a Hamiltonian version of the Disty equation, and they're reflecting the higher order dispersion and nonlinearity as well as you have your Hilbert transform term, which is the signature for the Disty equation, reflecting the presence of the induced mean flow. And so the I gamma U and the 2 gamma U sub X term, they are stemming from viscosity that was added into the Euler equations in the boundary, not in the Euler equations, in the boundary conditions that are used in the derivation of the viscous higher order NLS. And so this new here is, both of these terms are related to the viscosity that was put into the boundary conditions, but the new here is simply to turn on and off this U sub X term so that you can compare a linear damped NLS with viscous, linear damped higher order NLS with the viscous higher order NLS. And of course, this is a diffusive term that has been added in, and you'll see why. So in the context of these models, the linear damped viscous and diffusive viscous higher order NLS, we want to examine the linear stability of the damped Stokes wave solution. And we're focusing on 2 regimes. We're looking at the infinite time limit, where you see the destabilizing effects of viscosity as was observed by Carter and Gauvin. And we're looking at the short to moderate time dynamics, where you see the transition from an initial Benjamin-Feir instability to a predominantly oscillatory behavior superimposed on a much slower growth introduced by the viscosity. And so finally, we'll discuss the mechanism and timing of permanent downshift in the spectral peak and its relation to the location of the global minimum, the location of the global minimum of the momentum and the magnitude of its second derivative. Okay. Okay, so for the linear analysis, we have our damped Stokes wave. It's a solution of all three models, and doing your usual assumption of a small perturbation to this solution, substituting it into the viscous higher order NLS, we obtain the linearized viscous higher order NLS, and we have our usual, ansatz of a ingoing and outgoing waves for our modes v sub k. And here we are breaking those coefficients up into their real and imaginary parts. The coefficients A, K, and B, K are being represented in terms or expressed in terms of their real and imaginary parts. And so with this, you obtain a linear system of ODEs for those coefficients. But the important feature is that it is a non-autonomous system where you have this time-dependent term E of t, which is related to the linear damping. And you also, in the matrices, you have the term gamma here, which is encoding the viscosity effects. Okay. So before we look at the solutions to those analytical solutions to those systems of equations, let's just look numerically at what we anticipate that we would obtain. And so in the first row, first of all, we're looking at the long-time asymptotics right now. And in the first row of figures, you are looking at the case where there's no viscosity. So this is just a linear damped higher order NLS. And so the first plot is the amplitude, it's the evolution of the amplitude of A, and the second one is the evolution of the amplitude of B. And this is for k equals 1. And the initial data corresponds to having one unstable mode. The Stokes wave initially would have one unstable mode. And so you see that when the full viscous effects are neglected, that the magnitude of A and the magnitude of B exhibit purely oscillatory behavior for very large time. However, when you have viscosity, then the long time trend consists of that oscillatory behavior superimposed on a slow growth in B and a slow decay in A that's due solely to the viscous effects. So the reason that we have the two sets of figures here is because the first row corresponds to when the Stokes wave was initially unstable, and this was a stable case. Even in the case where the Stokes wave is stable initially, you still have the growth of these high frequency modes. Okay, so and so then the other regime we're interested in, the other regime that we're interested in is the short to moderate time, where we're looking at the transition from this exponential growth to the oscillatory, the predominantly oscillatory behavior on the slowly growing background. And so, okay. So going back to the system of ODEs, you see that the time-dependent coefficient here decays as t goes to infinity, it decays to 0. And so the long-time dynamics are governed by the eigenvalues of the M matrix, and they are of the following form, where you see that you actually have a real part. So in particular, then, for every eigenvalue lambda sub I, there's a solution xi whose norm is behaving like e to the gamma t for large time, And so in the non-viscous case, when gamma is equal to 0, all of the solutions of this system are bounded. But when you have viscosity, then there exists a solution, then gamma is non-zero. Then there exists a solution which grows exponentially at rate little gamma. And so, sorry for the bad notation, there's little gammas and big gammas. So again, here you see that viscosity is introducing these long-time instabilities into the dynamics. So, recalling that the form of the perturbation is actually the damped Stokes wave times this v of xt, then the large time behavior of the k-float is actually determined by plus minus little gamma minus big gamma. So if gamma is equal to 0, then your Stokes wave is then linearly stable as all solutions of the linearized linear damped higher order and less are bounded for all times, and they decay exponentially as e to the negative gamma t. But if you have viscosity, then a generic perturbation of the damped Stokes wave will grow exponentially. And you see from looking at your coefficient here, or your coefficient here, that the modes with k less than 1/2 epsilon will decay exponentially, while those with k greater than 1/2 epsilon will grow exponentially. So your damped Stokes wave is linearly unstable for any non-zero value of the viscosity. And it's important to note that the long time instabilities introduced by the viscous term are in the coefficient phi sub k, which correspond to the modes with the negative wave numbers. And again, this result will relate to the occurrence of frequency downshifting when viscosity is present as the amplitudes of the negative modes become dominant for large times, as observed by Carter and Bogan. So before we go to looking at the transition to from Benjamin-Feir to oscillatory behavior, let's just look at the effects a long time of adding diffusion. Your matrix, your M matrix becomes modified once you have included diffusion into the model, and subsequently your eigenvalues are also modified. And so the real part here now allows for the fact that once you've added diffusion, that there will only be a finite number of unstable modes instead of an infinite number of unstable modes. And if the delta that is being used is sufficiently large, if your epsilon delta is greater than 2 gamma, then the slow growth is completely eliminated. And the damped Stokes wave would be linearly a stable solution of the diffusive viscous higher order and less. And that's being shown here in these plots, where we're looking at the evolution of A and B with diffusion. And so you see that that slow growth has been eliminated. Okay. So now to model the transition from to model the exposition from exponential growth to oscillatory dynamics, we make the same assumption for our V sub k's, but we now leave A and B in their complex form, and you obtain this system. But you can, which at first looks a little intractable, but you can rescale and make substitutions to bring that system down to the second order ODE, which actually looks like it has an appealing form, right? The only wrinkle to it is the fact that the coefficient of U here is time dependent and complex. So, however, if you don't have viscosity, and so again, then that's when we're looking at linear damped higher order and less, then this ODE reduces to the following, and it has a real coefficient. So although U is complex, the equation has these real coefficients, and so you can use Sturmian separation theory to determine when the solutions are oscillating and when the solutions are exponentially growing, and find the transition time for that, to try to, and find the time when they transition between exponential and oscillatory behavior. So if your amplitude is small enough satisfying this criteria, then all of the solutions of the differential equation are oscillatory. And if the amplitude is larger, satisfying this criteria, then you're able to find this transition time where you transition from solutions that are exponentially growing for t less than t naught star and exhibiting bounded oscillations for t greater than t naught star. Okay. And so these are related to the results obtained by Harvey Seeger and their group, where they looked at linear damped in LS. And so here, the higher order terms in the linear damped higher order in LS, they're essentially increasing the instability of an initially unstable damped Stokes wave by effectively increasing its amplitude by this factor of square root 1 plus epsilon k. And they're also delaying the onset of oscillatory behavior. Okay, so now when we have viscosity, we have this genuine complex coefficient, but it can be transformed into one of the standard forms of Bessel's equation with the following transformation. And so the solutions, this is like your, what is it, your dying spring problem. Your dying, you have spring who's okay. And so the solutions to this equation can be written in terms of Bessel functions of the first and second kind of order nu, and the Henkel functions or linear combinations of them. And if you notice that your z variable here is small, because gamma is very small, then by using the limiting form of these Bessel functions for a small argument z, and for a fixed order, a complex order nu, but the real part of nu is positive, then you find the long-time asymptotic behavior is given as follows, which is describing oscillatory behavior superimposed on this exponential slow growth or decay. Right? And you can also determine the transition time for when you pass from this exponential growth to predominantly oscillatory dynamics. And the transition time, we're able to show that it's actually bounded between T naught star and T naught star plus some small constant. Okay, so moving along. So here this last topic is the numerical study of the effects of viscosity on frequency downshifting. And we want to examine the mechanism behind frequency downshifting, and we want to be able to estimate the time of permanent downshift. So I don't know, I mean, I don't know very many people are interested in the time of permanent downshift, but I haven't seen anybody discuss it. I don't know if it would be easy to determine in a lab tank, but that's one of the things we wanted to be able to do, was to estimate the time of permanent downshift. And so we're going to be doing this in the context of these three models. And the two quantities that are of interest to start with are the energy, the wave energy E, or the momentum P. And then we look at two different spectral quantities, the spectral center, which is also called the spectral mean, and the spectral peak, which are used to measure frequency downshifting. So this spectral center, and that's why the notation is K sub n, because it's the spectral mean. It's the average of the momentum over the energy, which when you give their Fourier representations, you see that it's really a weighted average of the spectral content of the wave. And again, as we started out with at the very beginning, the spectral peak is the wave number of the mode of maximal amplitude. So K peak corresponds to the highest energy mode at time t. So in the spectral mean sense, frequency downshifting occurs when the spectral mean is monotonically decreasing. And in the spectral peak sense, frequency downshifting occurs when K peak has moved permanently to a lower mode. And we are adopting the criterion that frequency downshifting occurs when both of these conditions are met. Some of the literature uses one, some uses another, some uses both, but we're using both conditions for determining frequency downshifting. And provided these two conditions are met, then we define the time of permanent downshift as the last time at which the carrier wave is the dominant mode. So the time of permanent downshift is the last time K peak is 0. Okay, so the spectral mean is a little bit simpler to get a handle on, because you can actually write equations for the change in the energy and the momentum and the spectral mean. And you see that in the case of the linear damped higher order and less, that's when nu is equal to 0. So you've turned off the full viscosity, and delta is equal to 0. So there's no diffusion. And so in this case, the derivative of the spectral mean is 0. So your spectral mean is constant. And you can also see that from the fact that the energy and the momentum change at exactly the same rate when you're looking at the linear damped higher order and the less. So there's no change in the spectral mean. So downshifting in the spectral mean sense will occur for the viscous higher order and the less, actually for all values of gamma, because EQ, this quantity EQ minus P squared here, is positive. And so your change in the spectral mean is always negative. And so you have you have downshifting for the viscous higher order NLS. And then diffusive viscous higher order NLS, it of course depends upon this coefficient here, PQ minus ER. And if it's negative, great, it decays faster, the spectral mean decays faster. And if it's positive, it just has to be smaller, which it typically is. This order epsilon squared delta term is typically smaller than the epsilon gamma term. So the bottom line is that for the viscous higher order NLS models, the first condition for frequency downshifting is satisfied for all gamma. So unfortunately, this equation for the spectral mean, change in the spectral mean, doesn't provide any information on the shifts in KP. And so one of the goals was to develop criteria which would specify if and when KP will permanently shift downwards. And so we're also going to make use of the Fourier representation of the momentum and the energy. And in the numerical experiments, we will find that the global minimum of P is crucial in determining the time of permanent downshift, and that the asymptotic behavior of the Fourier expansion of dp/dt gives a good estimate for the time of the global minimum of P. So the initial data used in the experiments are small perturbations of the unstable Stokes wave, and the amplitude and the period have been chosen. So the Stokes wave initially has two unstable modes. This is the specific initial condition that's used in this talk, but we have done it for an ensemble of experiments where you vary A and where gamma also has been varied from. This is the range of gamma used, and gamma is increased in increments of 2.5 times 10 to the minus 4. So this range of gamma was chosen because the study was also part of the effect of downshifting on rogue waves, and rogue waves don't occur in the viscous system for gamma bigger than 0.008. So we weren't interested in continuing it too much beyond that. Plus, it also has problems because of the instability from the viscosity. So if gamma gets too large. Okay. So in these plots, there's rather a lot going on. These plots are showing results for both the viscous higher order NLS and the diffusive viscous higher order NLS. The red curves are corresponding to the diffusive viscous, and the blue curves are corresponding to the data for the viscous higher order NLS. And we are giving the evolution of the energy, the momentum, and the spectral center for two different values of gamma for the two different models. And the value of delta chosen in the diffusive viscous case is sufficiently large that you have eliminated the high frequency instabilities. And so from the first plot and the third plot, you see that the energy and the spectral center are strictly decreasing for both the viscous and diffusive viscous models. And in fact, the energy qualitatively is very similar in its decay to the case of the linear dash higher order NLS. However, the evolution of the momentum and the viscous model is in striking contrast with the exponential decay that you would have obtained in the linear damped higher order NLS equation. We see that P achieves its global minimum at a time that we're going to call TP min, and it's then followed by a decrease in the magnitude of the momentum, which is important. Okay. So how does these changes in the energy and the momentum how does the change in the energy and the momentum affect the spectral peak? Well, here we have the evolution of the spectral peak for the viscous higher order NLS and the diffusive viscous higher order NLS. And we see that the decay in the energy coupled with that increase in the magnitude of the momentum during the initial stages or the early stages of the wave evolution results in this predominantly downward shift in K peak. But then because what we'll see is because the changes in the momentum become so small, it's not able to shift back up, which is why you have the permanent downshift. And here you see the evolution of the Fourier modes, and this is for the viscous higher order NLS, and you see that the negative modes are the modes that are becoming dominant. Okay, so here, since the momentum is so important, we have a plot of the evolution of the momentum, the derivative of the momentum, and the second derivative of the momentum. And so the blue and red portions of the graphs are marking off the time interval when K peak is 0 and when K peak is non-zero. And so for this example, and maybe since I don't have that much time, for this example, and exactly, you're going to see exactly the same behavior for all of the values of gamma. So, for the entire ensemble of experiments, the time of the global minimum is a precursor to the time of the permanent downshift. And so you have these rapid step-like changes in the momentum during the transition from K peak equals 0 to K peak non-zero. And these changes diminish in magnitude, which you can see in the derivative of P and the second derivative of P. These diminish in magnitude as time evolves. So the time of downshift occurs when the magnitude is strictly decreasing, and once P double prime is sufficiently small that the changes in P prime are insufficient for K peak to upshift back. And so to look at the, or to corroborate the observed behavior of P, we have that a rough estimate of the time for the global minimum of P can be obtained from the truncated Fourier expansion and of the PDT equals 0, and approximating the Fourier modes with their asymptotic expansion that we determined earlier, we find that the estimate for the time of the global minimum is being given as follows. And so the approximate estimate and the actual numerical time from the experiments are in very good agreement. And it's not just for this example, it's for the entire range of gammas that are considered. And so here we're looking at the dependence of the time of the global minimum and the time of downshift on gamma. And really the most important thing that well, first of all, you see the permanent downshift. And by this, I mean, in the KP, permanent downshift in KP occurs in the solutions across all initial conditions and for all gamma. And so the next most important thing is that as gamma increases, the time of permanent downshift converges or towards the time of the global minimum that you have here. So for the more reasonable, I mean, the larger, they're not large, if gamma's on the order of approximately 10 to the -2. For those values, the time of permanent downshift actually corresponds very closely with the time of the global minimum of the momentum. And so again, there's this very good agreement between the Fourier approximations of TP min and the numerical data. And so I guess I'll leave it there.
Kind of general question for bigger picture. Please correct me if I'm wrong, but my understanding all these pre-dissipation terms were kind of empirical. All these pre-dissipation terms which you use, they're kind of empirical, right?
Have you by values? Not derived.
No, they're not derived from something. They're more phenomenological. Right? Is that correct?
No, the terms in the Dispersive.
Yeah, they have three terms. Right?
It was proposed by Chamberlain and Zakharov that it can be modified the kinematic boundary conditions of the Bernoulli's equation by adding in viscosity. Then they said you would actually get the linear damping term on the MLS equation. And so the Coder go back and carry this calculation through for a higher layer. So the viscosity, forming viscosity into the higher order.
So I mean, these coefficients, these three coefficients for different dissipation terms were just given by physics. We are not fitting parameters.
So
I mean, there are three dissipation terms which show, right?
Yes.
One.
They're linked. And actually, I mean, some people have said to me that, oh, they like it because they're linked because now they only have one parameter.
Yeah, but I mean, but we're derived, we're not different. All the kind of three parameters for you to fit.
No, they were derived. And so the relationship between the inclusive X term and the gamma T term, there's a specific relationship. And that's in some sense kind of unfortunate because it could change it. I mean, I'm carrying through the calculation for higher order because we will get it. That's an inclusive term and get the derivation, but unfortunately, it doesn't actually not have the instability that you have that we see here at this level. And so it makes you wonder about.
But in such a case, if we derive, if we complete like some water tank experiment, will you would agree on? Or
I'm not an experimentalist, but part of the lab of conducted experiments where they have taken field, well, they didn't conduct experiments, they took field data. And they used this model for, for cooperating with data, except for the actual